Hi everybody, I hope this video finds you well. In today's video, we're going to be continuing on with our discussion of the two-sample mean procedures, and we're going to take a look at another example. So let's jump right in and take a look. So for this example, we're going to suppose that you work for a company that installs small auxiliary solar panels. And usually these panels save people an average of $105 per year. What you would like to do, though, is you'd like to run an advertising campaign that says your panels help people save more than $105 per year. So to do this, you take a random sample of 9 of your customers, and you get their yearly spending before installing their solar panels and their yearly spending after installing solar panels. And then you get the following data. We're also going to make a note here. We're going to assume that your company had around 10,000 customers to choose from when you chose those 9 to actually study. So you can see our data right here. We have our 9 customers, and you can see their spending before they installed the solar panels and their spending after they installed the solar panels. So what we're going to do with this is we're going to carry out at alpha equals 0.05 a hypothesis test to test the claim that people can save on average more than $105 per year by installing solar panels. Then we'll build a 95% confidence interval for the average yearly savings that come from installing solar panels. And then we're going to do a little bit of error analysis. We're going to try to determine would falsely claiming that solar panels save you more than $105 per year on average when they really do not be a type 1 or type 2 error, right? Remember, if you remember from the previous video, we did an example of looking at the type 1 and type 2 errors and just saying what they would mean. That's the pretty standard direction. This is sort of the reverse direction where we're being told a particular type of error and then we have to identify was it type 1 or type 2. So let's get right in and talk about the hypothesis test. So for part A here, we have to determine which type of hypothesis test we're going to be doing. Remember, at this point, you guys have 3 different hypothesis tests. You have the 1-sample mean, the 2-sample mean, and the matched pairs. So if we look at this, right, you can sort of see that we have these 9 customers and our 2 samples come from studying them before their solar panels and after their solar panels. And you can see that each data point is matched, right? This, for customer 1, they spent $980 before, and then we know that they spent $895 after. For customer 2, we know that they spent $700 before and then $608 after. So you can see that this is set up in a way that would fit a matched pairs analysis. Remember, a big tip-off for matched pairs is whenever you see something that has a before and after, or like a test 1, test 2 sort of structure. So for our hypothesis test here, this should be a matched pairs hypothesis test. When you're doing a matched pairs hypothesis test, remember, the actual data isn't going to be this sample or this sample. Instead, it's going to be the differences. So we need to calculate those differences. For the differences, we have 2 choices. We could decide to do the before and then subtract the after, or we could take the after and then subtract the before. It doesn't matter which way you do it. You can do it either way as long as you stay consistent. However, it'll probably be easier if when we do those subtractions, we try to get as many positive values as possible. If you notice, most of the before numbers seem to be larger than the afters. So it might be easier to do it as before minus after so that we can sort of see that every value as a positive value there. So we're going to do before minus after. So real quick, let's actually calculate those differences. We can just add an extra little column here, the differences. All right, so we can just subtract across. So we can just do that on our calculator. 980 minus 895. Looks like we should get 85 for the first one. Then 700 minus 608. That looks like it should be 92. Then 856 minus 721. Looks like we should get 135. 907 minus 807. 100. 658 minus 553. Looks like that should be 105. 498 minus 374. Looks like that should be 124. 876 minus 770. Looks like that's 106. 814 minus 702. That's 112. And then 758 minus 641. Looks like that's 117. So this right here, this is actually going to be the data set that we will be using. Whenever you have a matched pairs analysis, you are always going to be using the differences. Now, what do these differences represent? Well, since we did it as before minus after, these differences represent the savings, right? This first person apparently saved $85 because they went from $9.80 to $8.95. Whereas customer 9 apparently saved $117 because they went from $7.58 to $6.41. You can see that the differences are what we would be interested in because we don't care how much they spent before or after. Everybody uses like a different amount of electricity, but what we care about is how much money they saved, right? In other words, even though, this person here spends $807, right, which is higher than $608, they would be happier with their sort of solar panels because they saved $100, whereas this person only saved $92. So it doesn't matter how much they were spending before or after, it matters how different those two values are, and that's what we calculated. So that'll always be sort of a preliminary step whenever you're doing a matched pairs analysis. So let's go ahead then and get into the actual hypotheses. So the first step here, we've got to set up those hypotheses. Well, as always, there's going to be a null and an alternate. The way we set this up, though, is that since we are doing a matched pairs, right, the notation will be D equals some value, and then D with some inequality sign in that same value. So again, we still need to figure out the null hypothesis, and we have to figure out the inequality sign for the alternate. So let's go ahead and see. What is our baseline assumption here? Well, if we look through here, is there any sort of baseline assumption? Again, remember, anything for your hypotheses should not relate to your data. So we're just saying, is there any sort of underlying assumption? Well, we see right here, it says usually these panels save people an average of $105 per year. So if that's what usually happens, that's what we would expect for our company as well. So our null value here is going to be that 105. What is our claim? Well, if we look at what we're being asked, you can do that from the main text of the problem or just in part A here. It says you want to test the claim that people can save on average more than $105. So since we're saving more than that, we would use a greater than. This tells us that when we go to the p-value part, this will be a one-sided test and a one-sided p-value. So in other words, we're assuming that if our solar panels are just like everybody else's, people should save on average $105, but we're hoping that on average we do better than $105. Okay, let's go ahead and look at the conditions. Well, the first condition, as always, is that it has to be random and representative. If we go back up here, it does say that we randomly sampled 9 of our customers. So we've got that, that's stated. Put our little check mark there. Then we need to make sure that our sample size is less than 5% of our population size. Well, again, remember, sample size is something we will always know. Population size, we have to read through and see if that was given to us. Sample size, we know we took a sample of 9 customers, so we have a sample size of 9. And notice that there's a note here that tells us that we had around 10,000 customers to choose from, so that would be our population size. So we can actually check that. We can say n equals 9, and we can check, is that less than 0.05 times 10,000? Well, 0.05 times 10,000, that sounds like 500, and 9 is less than 500, so we're all good there. Okay, condition 3. Well, condition 3 is the one where you either have to have a sample of size 30 or more, which unfortunately we do not, we only have a sample of size 9, or we have to check that the data is normal. In this case, what do we mean by the data being normal? We actually have to check that the differences are approximately normal. Well, to do that, of course, we're going to have to take a look at our differences that we have here and do something like a stem and leaf plot to actually examine that. So, in terms of those differences, it looks like we've got stems of like 8, 9, all the way up to like 13. So, it looks like our stem and leaf plot should be 8, 9, 10, 11, 12, and 13. It looks like we have an 85, a 92, and 100, 105, and 106. Looks like we've got a 112 and a 117. And then we have a 124 and a 135. And I suppose we can put a little key there. 8/5 in this case means 85. Okay, is this the sort of thing that we're looking for? Well, again, it's not a perfectly normal shape, right? I mean, because it's only got 9 data points here. But in general, there's no strong skew, and especially important, there's no outliers. So no strong skew, check, and no outliers. So this is exactly what we're hoping for. Notice that when I did this, we again completely ignored the before and after data. Once you've calculated those differences, that's what you're going to be using for the entirety of the computation. So all we cared about was the distribution of the differences. Okay, so all the conditions are satisfied. We can move on to the test statistic. For our test statistic, the formula is going to be a t-test statistic. So whenever you're doing quantitative stuff, you always are using a t-test statistic. For that test statistic formula, it was d bar minus d over sd divided by square root of n. So there's 4 things that we need to know to plug into this formula here. We need to know d bar, d, sd, and n. If we think about these, some of these we've already mentioned. We mentioned n. We know that that's our sample size. That's 9. And we know d, that's the null hypothesis. That's going to be 105. D bar and SD, well, that just means the average of the differences and the sample standard deviation of the differences. So what that means is we'll take this data set that we have here and we're going to put this into L1 and then use our 1 var stat. And if we do that, we can go ahead and get ourselves our mean and our standard deviation. So let's go ahead and type that stuff in. If you have your calculator, you can go ahead and do that. So you pop in your 85, your 92, 135, 100, 105, 124, 106, 112, and 117. Then stat, calc, that 1 var stats. Go ahead and run that. And you want to just record those values there. So it looks like our average here was 108.44, and our standard deviation, make sure you grab the sample one, should be 15.58. Again, the only reason I'm keeping 2 decimals here, especially on this guy, I could probably just get away with 1 decimal. This is money, so it makes sense to keep 2 decimals since that would represent the cents. Okay, so let's go ahead and plug this stuff in. We would get T is 108.44. minus 105 divided by 15.58 divided by the square root of 9. Okay, once again, go ahead when you go to type that into your calculator and do the top and the bottom separately. So let's go ahead and do that on the next page here. So continuing on, so this is step, we can zoom in a little bit. This is step 3 continued. So remember right now we have T is 108.44 minus 105 over 15.58 divided by the square root of 9. So we'll go ahead and do the top and bottom separately. So 108.44 minus 105 is 3.44, and then divide by 15.58 divided by the square root of 9. Looks like we should get 5.19. Then go ahead and do that division. 3.44 divided by 5.19. Looks like we should get T to being approximately 0.66. Okay, so that is our test statistic. Now we are ready to go ahead and move on to step 4, the p-value. For the p-value, we will need to go ahead and use table C. We'll need to know our degrees of freedom, which in this case is our sample size 9 minus 1, which is 8. So we have our t-value of 0.66. You're going to be using degrees of freedom 8. And remember, we want the one-sided p-value because our alternate was one-sided. So let's go ahead. We're looking for 0.66 with 8 degrees of freedom. So our 8 degrees of freedom would be right here. And as you can see, the very first value is 0.706. But ours would actually end up being right here, 0.66. It wouldn't even make it on to the table. So let's follow that down. So we're following down this way, all the way down to where the one-sided p is. So we would be right over here. Now remember, the p-values get smaller and smaller as you go this way. So you could also say they get larger and larger as you go this way. So that tells us our p-value is larger than the largest one listed here, which is 0.25. So what we can say here is we can say that our p-value, even though we don't know exactly what it is, must be greater than 0.25. It must be larger than 0.25. Then we can go ahead and make a conclusion with this. Okay, for our conclusion, we can take that p-value, compare it against the alpha that was stated in the problem, which was 0.05. How does this p-value compare against that alpha of 0.05? Well, if the p-value is larger than 0.25, it is certainly larger than 0.05. So the p-value would be larger here. Whenever the p-value is larger, we would fail to reject the null hypothesis. So we failed to throw out the original assumption. That means we failed to find evidence. So we would say that there is no significant evidence for our claim. What was our claim in this case? Well, you can look back. Our claim was that the difference, or in this case, the average savings, is greater than 105. So we would say there's no significant evidence that, on average, customers save more than $105 per year. So in other words, we don't have enough evidence to say that people really save more than $105 per year. Does that mean that the panels don't work, right? That they don't save you money? No, of course not, right? We're just saying we can't claim that they save you more than $105 per year on average, right? So they might save you money, but they don't save you more than $105 per year on average. Okay, so this was your guys' first example of running through and doing a matched pairs hypothesis test. In this case, we found out that we did not have enough evidence to really say that our panels save you more than $105 per year on average. Why did we get such a large p-value here? Well, if you look back at the actual data, right, we were testing against a baseline assumption that you save 105. And in our data set, people saved 108.44. And basically what we diagnosed is 108.44 is not that different compared to 105, given the amount of deviation and the small sample size. So that's why we were unable to find evidence here. Okay, let's go ahead and move on to part B here and talk about building a confidence interval. So for part B, we're going to build a 95% confidence interval for the average savings. Now, the point of why we're going to do this is, well, we just found out that we couldn't say that you save more than $105 per year on average. But we might want to have a sense of how much on average can you save. Like we were just saying, just because you don't save more than $105 per year doesn't mean that the panels don't work. They certainly save you some money, just not more than $105 on average. So let's get an estimate for how much they do save you. So we're going to build a 95% confidence interval for the average savings. This will be a matched pairs confidence interval because we're going to be using the same data here. So we'll have to first start with the conditions. Conditions for the matched pairs confidence interval is the same as the matched pairs hypothesis test, so they're already checked. Okay. Then we can move on to the construction. The formula for the construction is going to be d bar plus or minus t star sd divided by root n. So 4 things here: d bar, sd, n, and t star. Remember these first 3, d bar, sd, and n, they all reference the sample, so we just carry over the values that we already had. Remember that d bar was 108.44, sd was 15.58, and n was 9. So this will be 108.44, this will be 15.58, and n was 9. How do we get this t star? Well, we can look that up on table C. We will use our 95% confidence, and our degrees of freedom, of course, is going to be 8. So we'll intersect those two things. Let's go ahead and do that. So 8 degrees of freedom right there. 95% confidence right there, 2.306. So our value there is going to be 2.306. So we've just figured out our t star, 2.306. Let's plug all this stuff in. 108.44 plus or minus 2.306, 15.58 divided by square root of 9. This, as always, is your margin of error, so go ahead and do that first. So do 2.306 times 15.58 divided by the square root of 9. That means we should get 108.44 plus or minus 11.98 after you round. Then go ahead and build your confidence interval. So 108.44 minus 11.98. And it looks on the low end, we should get 96.46. And then on the high end, 108.44 plus 11.98. Looks like we should get 120.42. So this range right here gives us what we think the average savings is. So we're 95% confident that average savings is between $96.46 to $120.42 per year. All right, now, as always, I want you guys to sort of see the relationship between the confidence interval and what we did in the hypothesis test. In the hypothesis test, if you go back, right, we had a null hypothesis of 105, and we were unable to throw that out. If you notice, right, in our interval, 105 is inside that interval. Now, 105 is one of the values that we consider believable based on our confidence interval. Since it's one of the values that we consider believable, we were unable to throw it out. So what the hypothesis test is telling us agrees with what the confidence interval is telling us. So these two procedures, even though they're different, they do show agreement. What this is basically telling us here is that we would be confident in telling our clients that on average, people save between $96.46 to $120.42 per year using their panels. Does that mean that 95% of people save this amount of money? Certainly not. Even in our tiny sample, there were people who saved less than that and people who saved more than that. Our point is that this is our 95% confidence interval for the average savings. Not for what individuals will experience, but what for the average of all of our customers together. Okay, let's go ahead and quickly talk about Part C. Part C said, we state you save more than 105 per year on average when you really do not. Okay, and we want to know, is that type 1 or type 2? Well, we can do that by remembering that type 1 is where you reject HO, but HO is true. And remember, type 2 is fail to reject HO, but HO is false. So, which one is this going to be? Well, to make this sort of error, we have to state you save more than $105 per year. If you go back to your hypotheses, the way we would say that you save more is by going with the alternate. Meaning the only way we would say that you save more than $105 per year is if we throw out the null. So this type of error here would be based on rejecting the null hypothesis. So what we're describing right here would be a type 1 error. So if we decided that you saved more than $105 on average when you really do not, that would be committing a type 1 error. Remember also, type 1 errors are supposed to sound like false positives, and that's exactly what we're seeing here, right? This is where we think that we have evidence that we do a better job than what is typical, but we really do not. That would be a false positive. All right, what's the sort of natural or the real life consequence of this? Well, I suppose this is where you would run a false advertisement, right? If you think back to how we sort of originally phrased this problem, we were saying that you wanted to run this advertising campaign that says your panel save people more than $105 per year. Well, committing this sort of error would be where you go ahead and you run that advertising campaign, but it's really not true. So you would run a false advertising campaign in this case. All right, so at this point, in this video and the previous one, you guys have seen an example of both of the new procedures you've learned, the 2-sample mean procedure in the previous video and the matched pairs procedure in this one. In our next video, we'll do a couple more examples, just helping you guys get some more practice with these and also making sure that we're comfortable with diagnosing which of our 3 procedures we're supposed to use.